was off. That's super loud now. It's going to feed back. Do you have? Are you better? Test, test. 1, 2. Are you? Yeah? More? Doing better? Doing better? I'm still getting crazy. Ringing, ringing, echo. Better, better. I could sing you all one of the lullabies I sing my daughter.
Okay, start.
All right. Good.
Start the singing.
My daughter's name is Viva. I sing her, Viva crying in the dead of night. Take this dirty diaper and learn to sleep. It's the story of my life. But we in the midst of all that, we missed the big reveal. So I did these two very simple changes here of just making them a little taller at the bottom and making them a little thicker. Okay, this doesn't look a bonsai tree, but the dang thing looks like wood, right? It looks like it's made out of wood. I mean, it's not super convincing. This isn't hyper-realistic. I know it's some kind of fakey simulation. But just messing with the thickness of the segments has suddenly created the impression, whatever this is, it's certainly not a little prairie weed. It's something kind of tall and twiggy. And it's interesting that what I did was mathy. I said, count number of descendants, find some function of that. The result is aesthetic. I respond to it by saying, oh, that's a different kind of plant. It's made out of a different kind of material. And that second reaction is fascinating, right? Because I didn't change the material. It's still this sort of smooth brown cylinder that's each one of these things. I did not change the material, but my brain is telling me this is made out of some different substance than this. Don't you? I mean, I have that reaction for sure. I didn't change the color or anything. This whole project is all about finding the one little trick that makes your brain think you're seeing something. So the next thing I do, this thing is called an L system. I changed it to a parametric stochastic L system. The reason we give things fancy names in math is that they're really stupidly simple a lot of the time, and it just wouldn't seem like we're doing any work at all. What I do is just randomly remove some of the segments while I'm doing the substitutions. That's it. There's a few details, but that's the result. What's the change? Here, I just apply the same substitution every time, everything growing up. Here, instead, as I apply the substitutions, at each step I say, I'm just going to throw a few of these segments away. So I've got, maybe here's 2 segments of the tree, and there's a third one up above. I yank this one out and join it to the one above it. And just that is sufficient to all of a sudden make it look like a tree. What I like about this, for the purpose of this app, is that it's really shrubby. This is a messy, ugly little tree. Because in that bonsai class, the thing that the teacher said is, oh, when we make a bonsai, no, it's not like some dwarf species or anything like that. We just start with a really dense little shrub that's kind of overgrown and has too much, and you trim it down. And he took tons off of that one that you saw. You start with something shrubby and trim it down until it has that nice sort of minimal bonsai feel. And now, notice that because I'm doing a bunch of things that are random, I'm randomly removing segments and I'm randomly doing rotations, I can keep making different trees. So the beauty of this app is that because the trees are algorithmically generated, we didn't just draw one in a 3D modeling program, there's a very, very large number of them, effectively infinite. I mean, computers have finite memory, blah, blah, blah. But there's an effectively infinite number of trees. So every bonsai tree you trim with this is yours. You're the only person in human history who will be trimming that tree. So when you pick one, make it beautiful. So there it is. We have something that now looks like a completely dead bonsai tree, which, by the way, is how ours ended up. We didn't do a very good job of taking care of it. we had an idea that you could take one of these home and like put it on an app on your own phone and then like keep maintaining it over time. And you could water it and it would grow and you could keep trimming it. But you know, it's a nonprofit budget, so that didn't happen. There's a very serious problem, though. Before we get to making the thing look alive, there's a very serious problem that I think will be obvious if I zoom in a little bit. And that problem is all of the seams are showing. You see this right here? That's really messing with the believability of this tree. That just, I mean, it kind of almost looks like a tree, but it's so obviously made out of a bunch of cylinders. Ugh. And it's the seams that do it, right? So what's going on here is that, no, I'm already in that one. I need this one. There we go. Oh, by the way, this is a bunch of other things you can do with the L systems. Pictures from the book. I forgot to mention, book has pretty pictures. Here's some of them. You should go check it out. Here's the problem that we're dealing with. This is why the seams are showing. This is kind of in cross-section, so each of these is a cylinder. There's these places where they just don't join up. It's especially places like this one right up here that look especially bad, where the rotation actually exposes a seam. And in particular, what's going on here, the way that this kind of 3D graphics work is it doesn't actually trace light falling through the air and casting shadows and all that kind of thing. No, no, no. We look at the shape of the thing, and whatever angle the surface is at, we use that to color it. Which means that in a spot like this one right here, depending on where it is relative to the camera and the light source, it's going to think that that inner part there should be super dark on one side and super bright on the other. If the light source is in the upper right, the renderer is just going to say, oh, that piece in the middle, it doesn't know it's in shadow. It doesn't know it's in a little valley. It says it's facing the light source. So what I need to do is draw a little light bit right next to a little dark bit. That's what's going on. That's why it looks so bad. With that in mind, just take another careful look. Yeah, that's not helpful, Mr. Computer. Thank you. That's the thing that's going on right here. We have two cylinders. There's a little tiny gap between them because of the rotation. And the top-facing part of the bottom one is showing up super bright. So there's an obvious solution for that. All I've got to do is go from cylinders to things with rounded caps, like I had in my first drawing. That's some mowing going on. That is some serious mowing. Right? This should do it, because now I don't have these deep shadows. Things look kind of smooth. Let's see what that looks like. Round caps. Whoa. What? Seriously, what? So what's going on here? Do you have a question, or are you just stretching? What's that? No, I haven't. It sounds. Oh man. That's totally what I'm doing. That's not. Do you know what it's called? Oh. Okay. I was briefly excited about it. I'll investigate. It sounds almost awesome. But yeah, what's going on here? So dark pieces, light pieces, white, but then this zigzagging, what the hell? So okay, these aren't really cylinders. 3D graphics is made out of triangles, nothing but triangles. Triangles are all we get to work with. Which means that when I make those rounded caps, they're not actually perfectly smooth little rounded semispheres. They're a bunch of triangles that make a mesh that's kind of like one of those geodesic domes or something. It's just my way of quickly approximating And one of the trade-offs in 3D graphics is that the more triangles you have and the smaller they get, the smoother they look, but the more time it takes to render, and this is on an iPad, so I can't use that many. The triangles are pretty big. By the way, if you ever wondered what trigonometry is for, that's it. This involved actual bona fide trigonometry, making the mesh. So I have this thing that's made out of triangles, which means that it's not quite perfectly smooth, which means that when you take two of these things and intersect them, you get a little bit of zigzagging where the differently angled triangles are meeting. It's kind of hard to picture, but there's a kind of a ridge between two of these flat triangles, and you have an up-facing ridge and a down-facing ridge alternating a bit, and we get that zigzag pattern. So that's a problem, and then the lighting makes it worse because remember, it has no idea that things in gaps tend to be in shadow. It thinks if it's tilted slightly up, I should make it lighter. If it's tilted slightly down, I should make it darker. So this perfectly reasonable thing that I did just made it worse. Right? This actually was less convincing than this. Right? So clearly, obviously, what I need to do is first merge all of those caps and then round off the edges just a little bit like that, right? From this to this. No, no, it's terrible. This idea, which is obviously correct, does not work at all. Why? First, the math of doing that in 3 dimensions is fantastically complicated. I have no idea how to do it, and if I figured it out, I could probably publish a paper about it. Finding, sort of minimal convex holes and meshes that make smooth surfaces to cover several, it's hard. And everything I've done so far has been actually relatively easy, right? I mean, some of the details are horrid, but the ideas are simple. This is I don't know how to do this. Furthermore, even if I could figure out how to do it, I wouldn't want to because I'm using a trick to make the rendering work on the iPad, which is that I'm using the same cylinder everywhere. I'm saying, hey, here's a cylinder, and I want you to put it here and 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 here. One of the big problems in 3D graphics is that there's data about where the triangles are that you compute on the CPU, and you have to send it to the GPU. Sending information from one part of the one processor to the other is very time-consuming. You want to minimize it. If I do this, I can't just have a bunch of copies of the same thing anymore. I would have to make one giant mesh that covers everything. If I did that, I would now have to send, instead of number of points in cylinder, I would have to send number of points in entire tree to the GPU, which I'm sure would bring the iPad to its knees. So I don't know how to do this, and I wouldn't want to, even if I could. It's so obviously right, and yet it's wrong. No, instead, I think, the thing I'm actually proudest of on this whole project. To understand this trick, you need to know a little bit more about this lighting problem I was talking about. So I said, remember, 3D graphics, most of the time, don't actually trace rays of light. They don't understand shadows, really. If you see shadows in a video game, they're computing it using some very, very, very clever trickery that has nothing to do with how light actually works. Usually. There are a few raycasted games out there, I think, but it's like magic future stuff. Now, the way that 3D graphics actually do lighting and shading is that when you send along the shape, you also send along with it the normals, which means I say, here's the shape, and here's a line that's perpendicular to it. And up here, a line that's perpendicular to it looks like this. Here, a line that's perpendicular goes straight up. I send that. I'm on the hook for computing it. That's where the trigonometry came in. But when I've computed it, I send it to the graphics card, and the graphics card says, so the normal's pointing that direction, huh? Well, my light source is over here, and I do some math, and I figure out that, I'm facing right at the light source. If this normal points right at the light source, then it should be kind of bright. And if the normal points away from the light source, it should be dark. And there's some details involved in that. There's different shading algorithms, but they all do that same basic computation. Does that make some sense? All I need to do is, I don't need to know anything about the whole shape. I just need to know what the normal is like at this point and how it relates to what direction the light source is in. So, to make those horrid seams go away, I do this. I lie. I send the shape to the graphics card, and I say, here it is, and perpendicular to it is still pointing this way, and it's still pointing this way. It's shaped like a round cap, but it's shaded as if it were going straight up and down the whole time, except for the top, which doesn't point any which way, so we're kind of SOL with that. What that means is that where two of these things join, I mean, so picture this. I guess I should have made a diagram of this one. It would really help you picture it. But picture two of these things joining, and picture that moment where there's kind of a gap. Like we have a curve going this way and a curve going this way, and there's kind of a gap between them. The shading problem is because I've got normals pointing this way right next to normals pointing this way. And if I make them all point straight out instead, in that same situation, then I've got normals pointing this way next to normals pointing this way. There's still a slight difference, but it's slight, it's small. So what does that look like? Since I keep proposing things and they're wrong, I hope there's a little suspense here. Here's the fake normals, bam. The shape has not changed at all. All I've done is change the shading. And you can still kind of see the seams, like there's just tiny shading differences here, but not really. At this point, our brains get super confused because the shading doesn't match the actual shape of the thing. You can see if you focus on some of these end caps as they move around, your brain keeps changing its mind about exactly how much curvature there is, because at this point we're lying about everything. The shading has nothing to do with the actual shape. This is I mean, we're so far from reality at this point. It's about convincing lies. This whole thing is about convincing lies. But now we solved that problem. There's no more seams showing. So now we're on to making it look like a live tree. And, oh, one other thing I do to make it just a little bit less ugly and cylindrical looking is that I just add some slight random bumpiness to the surface of this. I actually thought about doing bump mapping on this, but we didn't have time. So all I've done here is just made the cylinders a little bit lumpy so that they don't look so perfectly straight. And I think at this point it's not realistic. You wouldn't mistake it for a photograph, but it's convincing. I look at that and it's like, oh yeah, that's a tree. I can believe it. So let's bring it to life. The way to do that is, so it's funny, in computer science we talk about trees all the time, and it's a data structure, right? There's lists, queues, stack, trees. This is a tree, and it's actually a tree. Like there's a tree data structure that represents the tree. Of course, computer science trees, the roots are at the bottom, and the leaves or the roots are at the top, and the leaves are at the bottom, which my college roommate suggested was because I didn't get enough time outside. But what I do, I love the pun of it. I take the leaf nodes of the tree data structure, that is the ones that have no children. I take the leaf nodes and I turn them into actual leaves. Yeah, right? Which is kind of awesome, although the thing looks a bit like a Muppet now. So what did I do here? All I did was I have an image of a leaf, and I just yank out the cylinder. If it's a segment of the tree that has no children, no other segments underneath it, I yank that cylinder off and I put a leaf there instead. And it looks like this. Why? Because the leaves are all completely flat and they stick straight out at all angles. So yeah, leaves are not like that. So what are leaves like? Well, leaves like to kind of mostly be parallel to the ground, and also they're not rigid and flat like little pieces of construction paper. So let's just fix those two things. I'll make them mostly parallel to the ground, not perfectly parallel. If they're all exactly parallel, then it's just going to look weird. But notice they're still flat. They still look fake. But we're getting warmer here. And then this is the most confusing presentation I've ever done for the UI here, switching back and forth between Keynote and the iPad mirrored to the computer. It's more taxing than any of the code was. Here's my leaf image. Utterly rigid. So I take this and got a leaf like this. just curve it a little. And just curve it a little means that I have to find, either I have to go in with some 3D editing program and make a shape that I think looks like a slightly drooping leaf, or so I don't actually know how to do that because I'm not really a 3D modeler. So for me, I used some really highly sophisticated mathematical techniques to come up with a function that I thought had about the shape of a drooping leaf. So if I imagine the leaf stamped onto that curve, then I think it'll look like a kind of droopy leaf. The highly sophisticated mathematical technique that I used for this was that I spent about half an hour experimenting. And if it looked wrong, I tried something else. You know, while wrong, try other formula. Yeah. All the leaves are the same. So I spent a lot of time actually photographing trees and looking at trees and studying how beautiful and complicated they are and deciding which details to ignore. And one of the details that I ignored is that leaves have different colors. The new ones are slightly different. The dying ones are slightly different. The trunk has all of these beautiful colors running along the lines of the bark. You can see the little nodes of it. You know, my tree doesn't have roots. It's just too much. It's just too much for the thing to render, and certainly for me to code. Maybe if I were a graphics super genius, I could squeeze more of it in there. But this whole thing, you know, it's like the business with the light. It's about lying. It's about convincing lies. This thing is just not like a tree in any objective sense. But when I look at it, I say, oh yeah, that's a tree. Sure. That's what I'm going for. And so yeah, the leaves are all exactly the same on each of the 3 types of trees. It's the same leaf. So let's see. Oh, I did it right that time. Let's see what that looks like if I just add a little curvature to the leaves. And that's, I mean, it's such a tiny change, but I feel like this crossed some kind of threshold where all of a sudden I believe it again. Not that I'd be fooled, but if I want to believe it's a tree, it lets me believe it's a tree. And then the last thing I do is this thing is just so dense. That might actually be realistic, but it's just too confusing to trim something like that. I just randomly remove some of the leaves. And so here's a bunch of trees. Yeah, Luke? Randomly, just randomly. And that's all. Removing them is random. The curvature is all the same. It's the same curvature, the shape, it's the same leaf image. To draw this thing, I send the graphics card, actually a few different segments that are just very slightly different in their bumpiness. It's like the same basic shape, but with a few different variations in bumping. So I have like 5 or 6 of them, and they're also sized a little bit differently to handle taller or shorter segments. But I send a short list of segments, segment shapes, I should say, the leaf image, the curvature shape for the leaf, and then the coordinates of a bunch of individual segments. And that's it. It's actually a pretty concise list, which is why even my poor little iPad 4 can render this thing pretty smoothly. Now, there's a moment I love in a project when we go from working prototype of some of the code to the same thing with an actual design. And there's still, for all my years in programming, there's just something magic about having the dressing and the UI stamped on it. All of a sudden it feels real. Still the same tree, but here it is in an actual interface with the clipper image, which comes from an actual photo of real bonsai clippers. It's accurate. It's the one part of this that isn't a total lie. Yeah. When we were building it, one of the first things we were talking about, we sort of showed this concept, and one of the Como people said, oh yeah, so we have to make sure that the kids can't trim it down to a stump. And it's like, why? I mean, every kid will want to do this, and it's true. Like, if you watch anybody under the age of about 10 go up to it, the very first thing they do is trim it down to a stump, just to see if they can. And once they've established that nobody's watching over them and making them not do it, then because kids are much smarter than grown-ups about UIs, they immediately discover the undo button, and then they spend like the next 5 minutes making their masterpiece. But they always trim it down to a stump first. Always, like 80% of the time, trim it down to a stump first. It's fascinating. I could do a whole other talk on the sociology of watching people interact with this. When kids go up to it on their own, they're creative, they explore, they push the boundaries, they get really, really engaged. When they go up to it with a parent standing next to them, the parent's like, now touch here, now do this, now you do this, now trim that one. This control thing, it's just painful to watch. It's like, no, get away from your kid. We designed it. They're better at it than you are. You don't know it yet. Back off. Go play with the blocks, parent. But yes, I won that battle, and you can trim it to a stump. It's awesome, although it does remove it from the home screen after 3 or 4 slots. The ones that went down to stumps don't stay in the collection as long. I did change that. Don't tell the kids. So how are we doing for time? There's one more little awesome trick that I'd like to show. And this one, you have to have spent some time with linear algebra to understand the problem I'm trying to solve. But it is, so I tap the screen, and I want to know what to trim. You know, if I tap in a bunch of branches like this, how do I decide which branch got trimmed? Or even just more generally. By the way, this project had one of my favorite bug names ever, which was trimmed segments look like turds. So now I've put that in your head, and you'll start maybe kind of, but not really. Before, like they were a little more rounded at the end, and they kind of came to a point. It was bad. It was really bad. Yeah. But I wasted a good hour and a half on that. It was actually, it just involved changing the segment shape a little bit, but yeah. But no, there's this thing of just how do I know? I touch the screen. How do I know what I trimmed? Well, the intuitive answer is you trimmed that one right there that you touched. I can see it. But unfortunately, that doesn't work for code. What I've got in code is this big tree data structure, which is a bunch of composed matrix transformations. And I have separately the information about the cylinders that I'm dropping it into these different matrix transformations. So to get the place where I touched, I have to project a ray from the camera through the bonsai tree, find every cylinder that it intersects, and then find the closest one to the camera. And some of you haven't done graphics programming before, and you're like, okay, whatever. And some of you have done graphics programming, and you're like, God damn it, yeah. So in this case, the intuitive answer is totally the right one. How do I know which one I touched? It's that one I can see right there. Here's the thing. What I just described, projecting a ray to the camera, finding the intersections, figuring out which one is closest to the viewer, that's how it draws the thing. It does that for every pixel on the screen already. It says, okay, I'm drawing the tree at this point right here. What can I see at this point? Or what can I see at maybe this point where there's several things? Well, there's several polygons that are touching that point, and one of them is closest to the camera, and that's the one that I actually color on the screen. All of the logic that I need is in the graphics library, if only I can get at it. But here's the thing. That logic is happening on the graphics card, and it's being drawn to the screen. The logic is there, but I can only get its output as an image. I can't just say to it, which of my tree segments did I touch? No, I can say, what color is this pixel? Wait a minute, that's all the information I need. All I need to do is just draw it so that every segment of the tree is a different color. Then I say, okay, draw the tree like this. Every segment is its own color. And then I just say, what color did you make it right here? Then because they're all unique colors, I can look up the color of a given segment and say, what segment in my tree data structure did this color correspond to? And all I have to do is make absolutely sure that there's not more segments in the tree than there are possible colors, but there's not by a factor of many orders of magnitude. So that's it, problem solved. So every time you tap, I render this image but only for the one pixel that you tapped. And that's how it knows. And it's so much easier than doing all of this linear algebra. God, I'm so bad at linear algebra. The fun thing about this is that it colors them by numbering the segments. It traverses them in depth first order and just numbers them 1 through n, which means that as I trim them, the numbering changes. So if I trim the tree in this mode, it goes all Christmas lights. Woohoo! Yeah. So that's not there in the actual public version of the app. Sorry, it's too psychedelic for the public. Yeah. Sorry?
Are the pot and soil nodes on the tree?
They're just separate objects in the which I've. Yeah. No, it's the thing is, because I'm running this through the normal graphics pipeline, I have to say draw everything using this other coloring scheme, but I have to run the whole scene through it. So the pot just is in there, and if you touch the pot, it says, there's no segments with that color. What? Okay. And you'll notice that it's subtle, but it's not coloring the leaves here, because it turns out that the leaves just made it too hard to figure out what the heck you're touching. The way we wrote it is, whoops, I wanted it in this mode. While you're trimming, it gives you the X-ray view with the branches, and then when you hold your finger down, it gives you the full preview until you get to the potting phase. And there's some details here. I made some pots. They have a dirt texture. That dirt texture is just an image of dirt turned sideways. It's completely flat. It's a little hard to tell. But if now that I tell you to pay attention to it, you'll notice that it's completely flat. I make random pot shapes. There was a little math there, nothing profound. There's transitions between the close-up view for trimming and the potting view for, yeah, thank you, projector. That was awesome. I have no idea what just happened here. Yeah, that's all right. I was almost done with, yeah, okay. Computers. So here's a tree. And you can see the chain of trickery that gets me here has very little to do with either scientific modeling of trees or a list of requirements that I was given. So I said, I went to school and studied lots of cool stuff. And math class did not prepare me for this kind of thinking. Computer science did not prepare me for this kind of thinking. My experience working for Minnesota Public Radio and Oracle Retail and Garmin and all these, they did not prepare me for this kind of thinking. But I knew how to do this. How did I know how to do this? Because I'm a musician, and I also took composition classes, and I took a creative writing course. I took a bunch of humanities classes which dealt with aesthetics, and that's what we're talking about here. Aesthetics is emotional, subjective, cognitive response to our senses. I see something and I respond to it. I see something and I say, that's not a tree, that's a weed. Or I say, that is a tree. I believe it. That's totally a tree. This business of you don't know what the goal looks like, but you'll know it when you see it. It works if it feels right. That's something you can learn. It's a practice skill, and it's something that you learn from taking a pottery class. So I teach at McAllister in the spring, and I always tell students, hi students, if you're going to go work in software, just take at least one course that deals with aesthetics. Something in the arts, writing, something like that. It's relevant, and it's relevant in this profoundly important way that you think of, it's worth going back. You've all heard me give this spiel. It's worth going back to watch the video of Steve Jobs introducing the iPhone when it first came out, because he pulls it up and everybody's like, oh, the iPhone, it's real. We thought that name was so stupid, but now we like it. And then it comes up, remember that original iPhone interface, it says slide to unlock, and there's a little slider at the bottom, and there's the thing that he puts his finger on it, and he slides it over, and it follows his finger, and the crowd flips the fuck out. They're like, oh my God, and they're so excited about this, he has to do it twice. He just did the slide to unlock gesture, that's it. So why are they so excited? That's an aesthetic response. Something just happened. There's something about what he just did that made a light go on in everyone's brain that said, wow. What was it? I think it was, A, nice design. B, there's a lot of excitement. The context was positive. But C, touch interfaces, it's hard to remember, but touch screens at the time were terrible. One of the things that the iPhone did that's not widely noted or celebrated, it was one of the first touch interfaces where the latency was low enough that you couldn't see it. So when he slid that slide to unlock thing, it looked like his finger was actually moving it physically. And the aesthetic experience of it went from I am sending commands to software to I am directly manipulating something. And all this, people get so hung up on gestures in mobile interfaces. It's not about the gestures, it's the direct manipulation. The single biggest innovation of the iPhone was the scrolling. And not the coasting, though that was important, not the rubber band, though that's cool. The big innovation was the thing that happens when you have your list of email messages and you put your finger down and it highlights it because you're about to open it, but then you scroll instead. There's that little touch canceled dance that goes from the child view to the parent view where the scroll view can say, no, this is a scroll thing. Stop what you're doing. Stop selecting. I've got this. That little dance was a bit of clever API design, some clever technical trickery that let them create the aesthetic experience of scrolling is not pushing a scroll bar anymore. Scrolling is you actually just move the thing. And the latency was low enough, they pull all kinds of tricks, which are now not so necessary, but let me look at how UI table view is implemented. They pull all kinds of tricks with reusing textures on the GPU and doing God only knows what with the hardware of the iPhone to make it responsive enough and fast enough that you actually feel like you're pushing the thing when you scroll it. I'm all excited about this because I think it's cool, but also it made, remember when the iPhone came out and people were like, well, come on, they'll never catch Nokia. People really thought that, yeah. But they just created a superior aesthetic experience. And they knew it was superior because somebody at Apple, at least at the time, had really good judgment, aesthetic judgment. So this kind of thing, the bonsai tree is awesome. I wish I could always work on things that are just colorful and fun. But the principle applies to everything we design, everything we build that humans interact with. Aesthetics are always there. And I think actually aesthetics are more important than what we call requirements for a lot of software projects. I think I've said what I want to say. Are there any questions about the details of this? Yeah, Justin?
Yeah, is there any reason you apply textures to the
leaf the branches don't have textures. They're just solid colors. I had wanted to add a texture with a bump map, but I just found that's, I don't know, I didn't have time for it and it looked good enough. And so the thing that's not aesthetics but is good software dev experience is triage. Some things are too hard to fix. Some things are already good enough. I spend my time focusing on the problems that I can actually solve within the budget and the time constraints. And I do that until we run out of time and money. So that's kind of your answer.
I was curious, I noticed a very subtle line down the cylinders. Is that just in the few number of triangles?
Yes, basically. When you see a little line, it's your eye picking up the fact that the shading isn't perfectly smooth. And our eyes perceive nonlinearities or first derivative discontinuities in shading. We perceive that as lines when in fact what it is the shading's changing at this rate and then it's changing at this rate. You can even get a weird effect if you do a perfectly linear gradient in some circumstances from here's like white, sharp turn, black. You will actually see that bit of black, it'll look like there's a slightly light colored ridge along one side of it that's not there, and it's your eye trying to make sense of this discontinuity. Brains love to do this kind of stuff. Other questions about it? Yeah.
Did you know what interface it was going to be used on?
We decided on iPad very, very quickly just because it was good hardware and we knew how to work with it.
I guess did that sort of inform how you originally? Because you knew this one.
Yes. So all through this, I was checking the performance of the iPad and just verifying that, okay, I know it doesn't work perfectly yet, but if it did work, could the iPad handle it? And there were several points when I switched to fewer triangles or fewer nodes on the tree because it seemed to be working the iPad just a little too hard. I wanted to show some actual photos of it working in the space. Here's the kiosk as it runs, and here's the kids playing with it. Kids totally love it. I actually went to check on the iPads once and rounded the corner and heard a little, maybe 7-year-old saying to her mom, Mommy, my tree is in the virtual collection. Look. And I was like, oh, you can't script this stuff. Programming is awesome. But also, yeah, adults like it too. Don't tell anyone. You can download this on the App Store, by the way. It's free for iPads. It's called Make a Bonsai. And also, if you go to that URL at the bottom, you'll see our little Bust Out Solutions portfolio page about it. And there's a Get the App link right on that page, I believe. And if you want to learn more about me, that's my website at the top. We have, just a few more minutes? Yeah, 4 minutes. Or is it no, 11:15? Oh, I'm running over. I thought it was 11:15. All right, we're done. Thank you all so much.